Section 7.2, Definition of the Laplace Transform. The goal in this section, and really in this entire chapter, is that we want to be able to solve as many initial value problems of this general form as possible. So we want to look at problems of the form ay double prime plus by prime plus cy equals f of t, with the initial condition y of 0 is some given y naught, and y prime of 0 is some given y1. So here a, b, and c are constants that we know. The forcing function f of t is a function that usually we know, and the initial conditions are the initial values, y of 0 and y sub 1 are values that we know. Now we know that the method of undetermined coefficients is nice, and we've studied how to apply that and how to construct a particular solution of the non-homogeneous problem using this method. But in practice, we realize that it only applies to exponentials, sinusoids, polynomials, sums, products, and differences of these kinds of functions. So when it works very nicely, but it's not always applicable. On the other hand, the method of variation of parameters works for all f of t in theory, but the integrals involved in practice can be intractable, as we saw in a previous section. So our goal in this chapter is to invest in some machinery that will allow us to solve some very general classes of these initial value problems. So very general classes of forcing functions f of t. So to begin that investment, let's let f be a function defined on 0 to infinity whose range is the real numbers. We're going to define the Laplace transform of a function little f to be given by, and here's the notation, Laplace transform of little f of t is a function of s, and it's defined by the integral from 0 to infinity of e to the minus st times f of t dt. Let's call this equation star. Now the Laplace transform of little f of t exists whenever this improper integral converges. So at this stage, this is just a definition. We don't really know what it's going to do for us. We don't know what motivated this definition. So in order to appreciate what this is, we first need to compute it a little bit, understand its properties, and then see where it might take us. But for right now, I want you to think very abstractly that the Laplace transform is a transformation whose input is a function on 0 to infinity into r, and then the Laplace transform transforms this input function, little f of t, into this output function, which is going to be a function of s. You can see when you look at this that t here is our variable of integration. Here s is a different variable. So the t's are going to integrate out, and this will end up being, when it converges, will end up being a function of s. And so you input a function little f of t into the Laplace transformation. It outputs the Laplace transform of that function. So let's look at some examples. Let's find the Laplace transform of the very basic function f of t equals 1, where t is defined for values greater than or equal to 0. So just using the definition, and that's really the purpose of this exercise, is to acquaint ourselves with the definition and the calculations involved in that definition. So the Laplace transform of little f of t as a function of s is the integral from 0 to infinity of e to the minus st times my f of t dt. So the Laplace transform of the function 1 is we put a 1 in where we had our f of t. Now if you look at this from calculus 2, this is an improper integral. And so this improper integral is improper because it goes to infinity. So we're going to rewrite this as the limit as b goes to infinity of the integral from 0 to b of e to the minus st dt. This is now a proper integral. We just anti-differentiate and evaluate between limits. You do need to be careful because there are two variables here. S and t are both variables, so when you differentiate, you want to make sure, or anti-differentiate, when you do that, you want to make sure that you evaluate the t value between the limits, because that's the variable with which you're anti-differentiating with respect to. So when we anti-differentiate and then evaluate between limits, remember you want to do this calculation before you take the limit. The limit is going to be the very last thing that you do. We get this expression, and this we could simplify to this. Just take the minus is a plus, and e to the 0 is 1. And now if we stare at this, we said that the Laplace transform of our function exists only when the improper integral converges. So that means our Laplace transform is going to exist whenever this quantity is finite. So if you stare at this term, since b is positive, b is going to positive infinity, so b is a positive quantity. that if s is negative, then this function, this part of the expression, will become unbounded. So since b is already positive and b is getting large, we need s to be positive in order for this to be a decaying exponential and for the limit as b goes to infinity of this to exist. And when it does, it's going to 0 because it's a decaying exponential function. And so provided that s is positive, we get that this term goes to 0, and so this limit will end up being just 1 over s because this is independent of b. So our grand conclusion is that the Laplace transform of the function 1 is the new function 1 over s, with the stipulation that s has to be greater than 0. So the idea here is that we took a function in the t domain, this is f of t equals 1 in the t domain, we transformed it via this Laplace transformation, we produced a new function that has its own domain, its own range, its own graph, and we transformed this function into this function. Now we really don't know what that does for us yet, but it's sort of like when you were first learning differentiation. You would have an input function, say the square function, you would take its derivative and you would get an output function that was 2x. Or you would have an input function that's sine x, you would take its derivative and get a new function cosine x. So that was an example of the differentiation transformation. Here we just have a different transformation between functions, and it's the Laplace transform. Okay, so the idea is we feed in the function 1 into the Laplace transform, and it spits out the function 1 over s. Let's do another example. Let's find the Laplace transform of the function e to the at, where a here is just some constant. So following the definition, the Laplace transform of e to the at is the integral from 0 to infinity of e to the minus st times e to the at dt. We're going to rewrite this improper integral as a limit of proper integrals. And we'll go ahead and do a little algebra and combine the integrand to get this. And now we need to compute this, the integral of this proper integral. We need to compute this proper integral. And to do so, you could either do it mentally or you could do a little baby u substitution. So if u is minus quantity s minus a times t, then my du is minus quantity s minus a dt. So then I solve for my dt. My integral of e to the u times my du becomes this. And when the algebraic and the calculus dust settles, we see that a u substitution on this integral results in this as the antiderivative. Here's just the step-by-step work to do that. So let's just copy and paste this here, since it's the antiderivative of this. We'll evaluate between t limits. When we do that, we get this expression. And now stare at this in black. We want to see when this converges. We need this to be finite. This term is independent of b, so it's not really part of our analysis. So we look at this part and we say, well, in order for this to be finite, we know b is positive and getting large, so we need the exponent here other than the b. We need this exponent to be negative. For this to be negative, s minus a must be positive. If s minus a is positive, then s has to be greater than a. That will ensure that this is a decaying exponential as b goes to positive infinity, and when that happens, this term goes to 0. We simplify what's left, we get this, and so our grand conclusion is that the Laplace transform of e to the at is the new function 1 over s minus a with the stipulation that s has to be greater than a. Now we can just as easily compute the Laplace transform of a piecewise defined function, and you will see some of this in the homework and in parts of the chapter going forward, so let's at least practice that one time. So if we had the function f of t is t for t values between 0 and 1, so it's just the line y equals t on 0 to 1, and then it's 0 beyond that. And we don't really care what happens exactly at 1. You could make this an or equal to or make this an or equal to. It's not going to make a difference. Think of this as a switch. It sort of ramps up, and then at time 1 it suddenly turns off and it stays off. So we want to calculate the Laplace transform of this. Again, we're just going to use our definition. When we use our definition, since this is a piecewise defined function, we're going to break the integral up into two pieces, since this has two pieces. One piece is on 0 to 1, and on that piece, our function is defined to be t. And another piece is from 1 to infinity, and on that piece of the domain, our function is defined to be 0. So we just split the integral up, and it wouldn't matter how many pieces we have here. We just additively split it up over the relevant intervals. Now, if you stare at this, this is a proper integral, and this is an integral that you would do by parts. And so here I show the steps to do this by parts. And if you calculate this integral by parts here, you get this. And now this integral is very simple because this is 0, so we're just integrating the 0 function, so we get 0 for this part. So notice this did not even end up being writing out a limit as b goes to infinity, because we only do that on the part that is improper. This part was proper, so this is just a regular integration. This part normally would be improper, but we sort of got lucky here with the function being 0, and we didn't even have to work to calculate its integral. So now we've anti-differentiated here, and we've evaluated between limits. We finish off this second integral in the integration by parts. We do that, we get this. And notice there is no limit as b goes to infinity because we had no improper integral. We just algebraically simplify this. This is just a matter of cosmetics, and we end up with this as our Laplace transform. Now we could keep going and calculate the Laplace transform of many different functions, and I won't do that here. Several of these are in the homework, but the idea would be exactly the same as the same 3 examples that we've already seen. And that is, if we were going to calculate the Laplace transform of, say, sine bt, this is going to be a very important Laplace transform for us for the rest of the course. If you do that after you do the work where you just use the definition of the Laplace transform, the details are just how hard the integral is to do. This integral you have to work a little bit harder, and it involves integration by parts, and the same thing for cosine. But let me just say that when all of that algebra and calculus work is finished, you end up with the Laplace transform of sine bt, where b is a constant, is b over s squared plus b squared, with the stipulation that s is positive. And similarly, when you do that work for the Laplace transform of cosine bt, after that work, you end up with the function s over s squared plus b squared, with the stipulation that s is positive. Another popular function that you would want to know the Laplace transform is t to the nth power, where n is a positive integer. And so the Laplace transform of t to the n, this requires repeated integrations by parts. And when that is finished, you end up with n factorial over s to the n plus 1, with the stipulation that s is positive. Now in our textbook, they gather these together into a table because we're going to see that we access we use these very frequently throughout Chapter 7. And so we're just summarizing that in this column we have just our regular little f of t. In this column we have our Laplace transform of little f as a function of s. And just as a notational aside is that a common notation, you can write the Laplace transform of little f like this, but we also commonly refer to it as big F of s. And that's not to be confused with an antiderivative. And that should be obvious from the fact that we're using an s here instead of a t. But big F of s is another notation for the Laplace transform of little f of t. So as we saw in our first example, the Laplace transform of 1 is 1 over s for s positive. The Laplace transform of e to the at is 1 over s minus a. And similarly for these 3 that we just listed here. The textbook has some other things in our table. Don't worry yourself with these right now. We're going to talk about these in future sections. But for right now, we're beginning to generate a table or a list of known popular Laplace transforms. And as we build up more of this list, we'll see how that we can use this list to our advantage in certain types of differential equations problems. All right, so to better understand the property of Laplace transforms, notice we've not been doing any differential equations. So we're still investing in our machinery to understand what the Laplace transform is, what its properties are, and once we're well versed in those things, then we'll see how they can help us in differential equations. But it's going to take a little bit of time. So one important property of Laplace transforms is what was called in calculus the linearity property. When you can take an operation and break it up over addition and subtraction, and you can factor out constants, then these two properties together are called the linearity property. And the Laplace transforms enjoy the linearity property. So the Laplace transform of an f plus a g is just the Laplace transform of f plus the Laplace transform of g. And you can do the same thing with subtraction. So you can quote-unquote break up Laplace transforms over addition and subtraction. You can factor out constants. So the Laplace transform of a constant times an f of t is a constant times the Laplace transform of f. So Laplace transforms enjoy the linearity property. just like derivatives and integrals did, and limits did. So notice that now we can use the linearity property to find the Laplace transform of much more complicated functions. I mean, we could do this by the definition, but this is going to be very complicated. This is a function that involves a square, an exponential, and a cosine. So instead of working hard, let's work smart and say the Laplace transform of this function is, let me try to get these on the screen at the same time, the Laplace transform of this function, first off, by property 1, we can break up the Laplace transform over this addition and subtraction. So we can do the Laplace transform of 2 plus the Laplace transform of t squared minus the Laplace transform of 3e to the t plus the Laplace transform of 4 cosine 3t. And then we can use the second part of the linearity property to factor out constants. So here this is a constant. 2 is 2 times 1, so we can factor out the 2 and leave a 1. Here there was no constant, we leave it alone. We can factor out the 3, we can factor out the 4. And now look at this. Every one of these pieces, these basic functions that are left after we've readied things using the linearity property, these we can now return to our table, which we don't have this memorized or anything. We're just going to reference back to our table. And we know how to take the Laplace transform of 1. The Laplace transform of 1 is just 1 over s. And similarly, the Laplace transform using our table, the Laplace transform of t to the n is our n factorial over s to the n plus 1. The Laplace transform of e to the at, here our a is 1 over s minus a. And the Laplace transform of cosine bt, if you look at the table, is s over s squared plus b squared. So we're able to very quickly, using our work from beforehand and using our table, that we're able to quickly calculate these Laplace transforms. And you could leave it like this, or you could simplify it and make it look like this, or rewrite it and look like this. It makes no difference. These are just cosmetic. Our goal in this section really is to familiarize ourselves with the definition, the integral definition of the Laplace transform, understand its properties and its very basic table compilation. And then going forward, we want to build up a reasonably extensive table of Laplace transforms and eventually use those to help us solve the initial value problems that we stated at the beginning of the section. Now, it's going to turn out that it's going to take us a couple of sections to build up that machinery, but that's our long-term goal, and this is the first step towards that goal.